Okay, so I want to move on to another fun game. This is the triangle game. Who do you think is going to win, me or you? Yeah, great. Exactly. Well, okay.
Well, the house always wins.
The house always wins. So I've been going to my kids' classes for years, and after a while, I've been there so many times in so many grades, the kids realize any game I am doing is rigged. Yeah, when they're young, you can get away with it, but after a while, it's like, no, wait a minute. So suspend your disbelief and believe that maybe I'm giving you a fighting chance. So here is the triangle game. So we start off with an equilateral triangle, and we label the corners 0, 1, and 2. And then what we're going to do is we're going to subdivide the triangle however you wish into just smaller triangles. Okay? If you want, we'll later on just do it subdividing into smaller equilateral triangles. But I divide into a bunch of triangles. And then we're going to take turns adding labels. And there's a very small number of rules. On the bottom, I can only use the labels 0 and 1 because that's what the two corners are. On the right side, I can only use 1 and 2. And on the left side, I can only use 0 and 2. On the inside, I can do whatever I want. So down here, it's only 0 and 1. Here, it's only 1 and 2. Here, it's only 0 and 2. So that's a 2 there, that's a 1 there, and that's a 0 there. And then on the inside can be anything. So on the inside, it can be anything. So the way the game works is if one of the small triangles is labeled 0, 1, 2, I win. If none of the triangles are labeled 0, 1, 2, you win. Okay? So I'm trying to get one of the triangles labeled 0, 1, 2. You're trying to stop me.
Like each side gets a 0, a 1, or a 2.
Correct. And I want one of the small triangles to have all 3 labels. If one of the triangles has all 3 labels, then I win. If none of the triangles have all 3 labels, you win. Okay? Who do you think is going to win? Me. So we have to try to find a way to make this game reasonable, right? Right? So I just put in a couple of, I just put in a random labeling here. So you can see on the bottom, it's all 0s and 1s. On the right side, it's all 1s and 2s. And I shaded in all the triangles that had 3 different labels. So this triangle over here has 0, 1, 2. And so I shaded that in. This triangle over here is just 1, 1, 2. So that would not be shaded. So does everybody understand the rules? I'm sorry?
No. Can you ever have one that's without 0, 1, 2? Like, is it possible for you?
Well, so that's the question is, I've been playing this game for years.
Yeah.
So maybe I'm just better because I have all this experience. But maybe if I were to play, I don't know, somebody who didn't find out the rules of the game 20 seconds ago, maybe they could actually beat me. So let's try to make it interesting. I'll put some money on it. So I will play one of you right now. And by one of you, I mean one of you will just be the public voice for the group. Everybody can input. If you beat me, I will give $40 to everybody in the room. But for every move you get, I get a move. If you get 2 moves for every move I get, I will give everybody in the room $20. If you get 3 moves for every move I get, I will give you $10. If you get 4 moves for every move I get, I'll give you $5. If you get 5 moves for every move I get, I will give you $1. And I will allow you to bank moves. So for instance, let's say you get 4 moves for every move I make. You make 3 moves, and maybe you keep 1 move in reserve. I then move, and now you have the 4 moves you would do, plus the move you kept in reserve. I will allow you to bank. So who wants to be the voice of the class? I couldn't tell if somebody volunteered or was saying not by how they moved their finger. Yeah, that's what I thought. I thought that's what it was.
What would we be labeling a vertex?
So you have to choose how we label the vertices. So I just need somebody to be the voice of the class.
I can do it.
Okay,
Really.
okay, so you are the voice of the class. So now, class, do you want to play for $40, $20, $10, $5, or $1?
Like 5 or
That's where I was
yeah.
like, well, I feel like we don't have a chance. We have no idea what's going on. So.
Yeah, hello.
So is $40 going to really make a big difference in your life? No. Is $1 going to make a big difference in your life? No. But you have the possibility of beating me. So do you agree that you can't do worse because you can bank moves? Because in the worst case, you just don't use moves. So your chance of winning can't be worse if you do 5-1. It may not be better, but it can't be worse. Again, this is the type of analysis you want to do. Sometimes it's actually bad to have a move, because whoever moves first could actually destroy a symmetry. But so over here, because you can bank moves, there's no difference between the 5-1 and the 4-1. But you just would make less. So what do you want to play for? What level? $5. So you get 4 moves to every move I do.
He's not pretty good.
I'll give you $5. I absolutely give you $5. So I have labeled the vertices A, B, C, D, E, F, G, etc., 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 to make it easy to determine. Do you guys want to go first or second? I'm being really generous. First. So you have up to you have up to 4 moves.
Are we just saying like A is 1?
You don't have to move at A first. You can move anywhere you want. You can
But that's the gist.
yes,
of it.
yes.
I feel. Do you just make like one of the sides like all one of the numbers, so that way
We could try that.
there's like less.
We can play more than one. So you want to make all the bottom. Do you want to make them 0 or 1, or it doesn't matter? Doesn't matter, right?
Is that 3 of our turns?
That's 3 of your turns. So I'm going to just pull them in as red.
That's how he wins.
Yeah.
No, and this is why I said earlier, when Mary walked around, it just stopped.
Vibration.
Yeah, and this is.
No, they knew it was rigged.
Okay. So let's just say, again, just for the interest of time, you chose 3 of your moves to be all 0s on the bottom. Do you want to use your 4th move now, or do you want to keep it in reserve? Bang. So I get a move right now. Yes. I am going to choose to put a green. Yeah, well, I get a move. I'm going to put a green right there. You now have 4 new moves plus 1 move. So you have 5 moves that you can do.
So that right, G.
Yeah, G.
Yeah,
G.
fix that.
I gotta make it a.
The G can only be a 1 or a 2.
Oh, right.
So do you want to have it as a 2? That would be deadly. So you clearly want to do that for one of your moves, right? So you've got 4 moves left.
Yeah,
Okay, so in F,
yeah.
what do you want to make F?
I don't know yet.
Well, yeah.
Well,
Yeah.
F could be blue, but if you make F blue,
Then that E open for.
it makes E open, which is dangerous. But of course, if you make it red, then I'm threatening here and here.
Yeah. Arguably. Yeah. Okay, so maybe 3-0 gotta do this.
No, but it's, again, I don't want to spend too much time on this.
Yeah.
It's okay if you lose. Yes, it is. Trust me. So give me a choice for F. We know it can't be green. It's either gonna be red or blue. Awesome.
It's okay.
We need F to be either red or blue. What would you like to choose?
Red.
Go red. All right. So we choose a red here. You're now down to 3 moves. What should J be? Not green. So your only choice is that has to be blue.
No,
No.
because then
Yeah.
you win. Yeah. Sorry.
Sorry. So okay, so good. So if it's blue, I win. If it's blue, I win because I would have that triangle, right? So if it's blue, I win. If it's green, I win.
Red.
So what do we decide about making F red? That was a bad decision, right? So F can't be red. So what should F be? It has to be blue. You might still lose, but we know you're going to lose if you make F. So E can't be green.
Yeah. No, it could be red.
It could be red. It could.
We don't have enough space to block.
Well, you've still got, I think 3 moves. You still have 3 moves left. So you want to make J red? J can't be red. J can only be green or blue. So you're okay.
But if you make E or E can't be green.
So you don't want you guys don't want me to have the ability to move at E.
Right. Yeah.
So you got to choose something
Or
for E.
J.
Or J. Well, no, J is not gonna.
It's fine.
J is fine.
Oh, just kidding. Never mind.
Yeah. In fact, you're not really too worried about J right now
On the other side.
because you know L can't be red. So J you don't have to worry about.
It has to be blue.
Okay, why can't E be red? Okay, E can't be red. We'd have to know. Can't be green. Good. So we know it has to be blue. Excellent. So good. So we know that has to be blue. So now you're down to 2 moves.
So now we have something to D.
Has to be an answer.
Yeah, it's red. Because it can only be red or red. On the side.
Well, here let's look. We know H. What does H have to be? What does H have to be?
Green.
H has to be green or I win. It has to be either green or red. So we know you have to use one of your moves to make H green. So now you're down to 1 move. And so now what does D have to be? If it's green,
You win.
I win. And if it's red,
You lose. No, you win.
It's either red or not.
so if you make this red, I've got those 3 in a row. If you make it green, I have those 3 in a row.
We lost.
So no matter what, you lost.
Yeah.
Okay.
We were even.
Nope. No, because the way it works. Here's a new version. I will give you a penny if you beat me. And I will let you have all the moves of the game. I won't move at all.
Can we switch like roles?
No. So if there's any triangle with all 3 labels, I win. And I will let you have every move. So what do I know must happen? It's not possible. I know there has to be a 0, 1, 2 triangle. Now, right now, this is hopefully a fun game. Nobody hopefully has any idea why we would care about this. There's actually a Nobel Prize behind this game. It's related to some really important stuff, which we'll get to later. So one of the goals of this is to try to give you stuff that you can bring back to your classrooms. Frequently, we are asked to do the wrong problem first. We should not be playing the triangle game. We should start off with a simpler game, the line segment game. And the way the line segment game works is if there's a 0, 1 segment, if a 0 is next to a 1, I win. If not, you win. Do we agree that this is probably going to be easier to analyze than the triangle? So let's start going from the left. You want to prevent me from getting a 0, 1 segment. What do you have to label the neighbor of 0? 0. Otherwise, you lose. What do you have to label the label? What is the label of the neighbor of the neighbor of 0? And as you keep marching like this, you see everything has to be labeled 0. But of course, we could have started on the other side. And if we started on the other side, what would the neighbor of 1 have to be? And the neighbor of the neighbor. And so you can see that as you march down like this, eventually you get to a vertex that has to be labeled 0 or 1. I'm sorry, labeled 0 or you lose, labeled 1 or you lose, and you can't do both. So eventually you lose. So this proves that the line segment game is rigged against you. This is a proof. I went to a wonderful university as a postdoc for a little bit over a year. They have won a national championship recently. They have done quite well in the college championship series for a long time. They did not win this year, unfortunately, but their conference did win. Anybody know what school I'm talking about? No. They have 4 words in their official name. The Ohio State University. Not a Ohio State University, the Ohio State University. In mathematics, we normally do not talk about the proof of a result. We talk about here is a proof of a result. There is more than one way to prove something. This is a valid proof that shows the game sucks for player 2. No matter what player 2 does, they're going to lose. There's going to be a 0-1 segment. I'm going to show you a better proof that player 2 is always going to lose. And so again, marching over. So let's look at a wonderful concept called a monovariate. So a monovariate is a quantity that only can change in one direction. So it can't go up and down, either stays the same and goes up, or stays the same and goes down. Can somebody give me something about yourself that only changes in one direction? Age. Age is the first one that people always say. And something that can go up and down. Weight. Or height. As some of us will start to realize in a few years. Most things can go up and down. It's very useful if you have a quantity that can only move in one direction. And so what we're going to do is we're going to do an example of a parity argument. You're even or odd. So one of the most interesting ways to prove that something exists is to count and show that the count is greater than 0, right? If the count is greater than 0, then it exists. If you can prove that the number of objects is odd, then there must be at least one element. There must be at least one thing that has that property if the number of things with that property is odd. If I know that the number of things with the property is even, there could be none. But if I know it's odd, there has to be at least one. And if people are interested in stuff like this, there's a whole slew of problems you can solve using these even-odd arguments. So let's look at the 3 different types of segments. We could have a 0, 0, a 0, 1, or a 1, 1. I'm not considering the 1, 0 because that's really the same. It's just flipping it around. And I can look and see what happens if I label a vertex in between. And so I could label a vertex between the 2 zeros with a 0 or a 1, between the 0 and 1 with a 0 or 1, between the 1 and the 1 with a 0 or 1. And let's count how many 0, 1 segments I have. So initially, I had none. I had none here, I had 1 here, I had 1 here. I'm sorry, none here. Correct? If I now go and put in the 0, how many 0, 1 segments do I have?
0.
0. And if I go and I put in a 1, how many do I have? Nope. 2. I have 2. In the second case, if I put in a 0, I still just have 1, 0, 1 segment. If I put in a 1, I still have just a total of 1, 0, 1 segments. In the last case, if I put in a 0, how many 0, 1 segments do I have? 2. And if I put in a 1, 0. So you change the number of 0, 1 segments by an even number. So if you look at how things were when we started with a 0, 1 segment. With all the vertices unlabeled in between, we had an odd number of 0, 1 segments. So as we go through the game, as we label all the vertices, we know at the end of the day, we're going to have an odd number of 0, 1 segments. So not only does the 0, 1 segment exist, it's odd. The number of them is odd. So we can prove that the number of 0, 1, 2 triangles is odd. So I'm going to try to do an advanced math proof on the spotter. There should be at least one moment in the class where you really stretch yourself. But this will show why the game is rigged and why I'm willing to give such high payouts. And I'm not that worried. So we have our 0, 1, and our 2. So when we look at the triangles, let's let P 0, 1, 2 be the number of 0, 1, 2 triangles. Does everybody understand what T0, 1, 1 would be? The number of triangles where one vertex is 0 and then the other 2 vertices are both 1s. So I have a lot of different triangles. Which triangles can give a 0, 1, 2? So which triangles can give a 0, 1 segment? So triangles with a 0, 1 segment. So does everyone agree that if I have a triangle labeled 0, 1, 2, it's going to have a 0, 1 segment? If I have a triangle labeled 0, 1, 1, it's going to have a 0, 1 segment. Are there any other triangles that I have to worry about?
0, 1, 0.
0, 1, 0. And let's just do it 0, 0, 1. So could any other triangle have a 0, 1 segment? No. So I only have to worry about those. If I have a segment inside, let's say this is a 0, 1 segment. How many triangles is that 0, 1 segment in? 2. If I have a 0, 1 segment on the bottom, how many triangles is that in? 1. So what I'm going to do is I'm going to count how many 0, 1 segments I have. How many 0, 1 segments does the T 0, 1, 2 give us? 1. How about the 0, 1, 1? How many does that give?
2.
So these give 1, and this gives 2, and this gives 2. So everybody agreed that if I have a 0, 0, 1 triangle, it gives me 2 segments?
That are 0, 1.
That is 0, 1. So let's look and count how many 0, 1 segments. So if I look at all the T1, 2 triangles, how many 0, 1 segments does that give me? Each triangle gives how many? So if I give you a triangle labeled 0, 1, 2, how many 0, 1 segments does it have? 1. If I give you a triangle labeled 0, 1, 1, how many does that give? 2. And if I give you a triangle labeled 0, 0, 1, how many does that give you?
2.
Does this count how many 0, 1 segments I have?
No,
No. Why not?
they could be sharing a 0, 1 segment.
Yeah, so any interior one is counted twice. So this is going to equal 2 times the number of interior 0, 1 plus 1 times the number of the boundary. Right? Anything inside is included in 2 triangles. So it's counted twice. Anything on the boundary is only counted once. Okay. Can somebody tell me what kind of number 2 times an integer is? Even. And 2 times an integer is even. 2 times an integer is even. What do we know about the number of 0, 1 segments on the boundary? Has to be odd. That's what we just proved. We started with an odd number, and then every time we labeled a new vertex, we changed the number either by 0 or 2. So if we start odd, we stay odd. So this is an odd number. So something plus even equals even plus odd. What's the only possibility for this? Has to be odd. So the number of 0, 1, 2 triangles has to be odd. There has to be one triangle with all three labels. I don't know where it is. This is a non-constructive proof. So I want to be very careful. I do not want to go deeply into politics. Does anybody know what's going to happen in 2028? Last time it happened was 2024. Last time before that was 2020. There's going to be an election. Imagine I have a consulting company and I go to somebody and I say, I can prove that you have a path to win the presidency. What are they going to ask me? Nope. What are they going to ask? Nope. I have a path for you to win the presidency. What are they going to want to know?
How certain?
100% certain.
That's what you want to charge.
Something else. Okay. I'll charge $10. What are they going to want to know?
How do you do it?
Oh, it's an existence proof. I can prove that you have a path to the presidency. I don't know what the path is. I just know that there's a way that you can win. It's a mathematical certainty. That's essentially what we have here. I can prove that there's a 0, 1, 2 triangle. It's a non-constructive proof. How many of you have taught calculus? How many of you remember taking calculus? So you might remember things like the intermediate value theorem or the mean value theorem, where you can prove that there are certain points that have certain properties, but you don't know how to find them. And so similarly here, I can prove that there's a 0, 1, 2 triangle. I can't find it, but I know it has to be there. And so this is a really good point to emphasize with students that sometimes in math, we can prove something exists without being able to identify it explicitly. And there's a whole school of mathematicians that don't like proofs like this. They don't like non-constructive proofs. If you're gonna, yeah.
It's me.
I don't blame you. I'd love to know how to find it.
Yeah.
That's why I'm only charging $10. And so I'm going to skip the fixed points right now. Because I don't want to get into too much detail. How many of you have heard of Nash equilibrium? Okay, so John Nash won a Nobel Prize in economics for work he did in game theory. This was his thesis when he was a graduate student at Princeton. It's like 20 pages, double-spaced. Doesn't have to be long to be impactful. And what he was able to prove is that in a lot of multiplayer games, you can be in a situation where no player has an incentive to unilaterally change their strategy. And unfortunately, what this means is you can get into situations where everybody would be in a much better spot if they could trust each other to move together. And so one of the most famous examples is the prisoner's paradox or the prisoner's dilemma. How many of you have seen this? So you have two people who are thought to have committed a crime. And they're going to be interrogated separately. And they're going to be given a deal. If you turn on your partner, I'll give you a reduced sentence. If your partner turns on you and you don't, I'll give you more. And if you're both quiet, you'll get a little bit less. So the payoffs are as follows. So if neither person confesses, each person gets 2 years in jail. If you don't confess and your partner confesses, your partner is going to go free, no jail time, and you get 9 years. Conversely, if you confess and your partner doesn't, you go free and your partner goes to jail for 9 years. And if you both confess, you both go to jail for 5 years. So the net amount of jail time is 10 years if you both confess 9 years if only one of you confesses, exactly one of you confesses, and 4 years if neither of you confesses. What's the best for you and your partner? Both of you should not confess, right? So what do? You're now in the room and you have the offer. You can confess or you can stay silent.
Right, if you confess, but yet you don't know if your partner's gonna stay quiet or not. So that's
So-
a gamble.
So there's a gamble. So if you confess and your partner confesses, what happens?
5 years.
You both get 5 years. If you confess and your partner doesn't confess,
You go free, they get none.
you go free, they get nothing.
Yeah.
Right,
I'm sorry?
You're risking it.
You're
for 3
risking-
years.
Right.
yeah, because you're risking if the person's gonna talk or not.
But you don't know what your partner's going to do.
Right,
If you knew for certainty that your partner would not confess, what would you do?
yeah,
Not confess. And if your partner knows that you're not going to confess, what should they do? Screw you. We're probably not talking about nice people there. They're being interrogated for a crime. It depends. So if you are sure that your partner is going to be true and not confess, is it in your interest to confess?
Probably, yeah.
Yeah.
Well, if you confess, then you both get 2 years.
No. if
Oh,
you
sorry.
Yeah, you go free.
Yeah. So sorry. So if you confess and your partner doesn't confess, sorry, if your partner tells you I'm not going to confess, you can trust me, pinky swear. Right? I'm not going to confess. Okay, you're not going to confess, I won't confess either. And then we commit the crime, allegedly, and are being interrogated. And my partner has told me that they are not going to confess. They pinky sweared, I trust them. If I know they're not going to confess, should I confess? That gets me off. And then my partner makes the same calculation. And so in a situation like that, there's a tremendous pressure for both people to confess, which would put you up here with 5 years of prison time for both of you, for each of you. It would be much better if both of you held and didn't confess. But if you don't know for sure what your partner is going to do, there is an incentive for you to protect yourself. So it turns out analyzing stuff like this is related to what's called finding fixed points. And so I know some of us either have drinks, like if we're reaching at the right time and sitting here. It's often called the coffee theorem. So we will assume no real world physics. We're not going to have atoms and stuff like that. We're going to assume coffee is continuous, which for some people is not an unreasonable assumption. And we will assume you mix your coffee continuously, and then it eventually settles back in the cup. The coffee theorem says that 1 point of coffee returns to where it started if you mix it continuously. If I don't mix things continuously, it's easy to violate this. What I could do is chop off the bottom third, put that on the top and slide everything down. Then no point is left alone. That's not a continuous mixing motion. In any continuous mixing motion, 1 point has to return to where it started. The triangle game that we were playing, that's rigged, it turns out the fact that there's always a triangle labeled 0, 1, 2 means that if you have a map from the triangle to the triangle, there's always 1 point that's not moved by the map. And that's extremely valuable for lots of things. So part of today is to just show you some advanced stuff. So
I'm confused by that map. Can you say that right again?
yeah, so imagine we often have maps from, say, the real line to the real line. I could have a map that takes a point in the triangle and it associates it to another point in the triangle. And what I'm saying is, if you have a map like that that's continuous, there will always be 1 point that's not moved. So as long as I have some nice conditions. So we say x is a fixed point if f of x equals x. The input is the same as the output. Most points are not fixed points. but every now and then you have a fixed point, and it turns out that these are very useful. So we wonder, why do functions have fixed points? Why do we care? So any continuous function from 0, 1 to 0, 1 has a fixed point. And so the proof of this, I can actually do very quickly. 0, 1, 0, 1. So I'm mapping the interval to the interval. If f of 0 equals 0, do I have a fixed point? Yes. So we'll assume f of 0 is not 0. If f of 1 equals 1, do I have a fixed point? Yeah, so we'll assume f of 1 is not 1. So maybe f of 0, it's going to be a little bit larger than 0, and f of 1 has to be a little bit smaller than 1. And I have a continuous function, so you give me some x, and I go up to some point. So maybe that's my function. So here's my function f of x. Here's the line y equals x. And if the blue line hits the red curve anywhere, I have a fixed point. And so it looks like I actually have two fixed points, two inputs that are unchanged by the map. One way to think about this, if I start off at a positive height and I end up at a negative height, at some point I was at height 0. This is the intermediate value theorem. If I start 2 miles from home and I end 1 mile before home, at some point I must have gone through home if I live in a one-dimensional world. Yeah. So in this case, I can show you without too much trouble that this function has to have a fixed point. It turns out that it is very useful to be able to find fixed points. So imagine I want to solve the equation g of x equals a for some function g and some number a. And imagine I have a way to find fixed points of functions. So if I ever become royalty and I get to have a coat of arms, I'm going to have a hammer on it. Does anybody know the law of the hammer? If all you have is a hammer, every problem looks like a nail. If you listen to any presidential debate, it doesn't matter what question they're asked. They meander for about 30 seconds and they go into their fixed spiel. They had a couple of things that they wanted to say, and they find a way to do it. And depending on how good the politician is, the transition is more smooth. But if you're good at something, if you can do something, you try to take whatever you have and convert to what you're good at. So if I have a way to find fixed points, I can convert this to a fixed point problem. So I want to find a value of x such that g of x equals a. So you give me a function g, you give me a value a, I want to solve this equation. So hopefully you have all been in situations where you are teaching students, we want to solve equations. This is something we need to know how to do. So let's let f of x equal g of x minus a plus x. I'm going to look at this as a new function. And so we often put a colon to the left of the equal sign to say that this is a definition. I'm defining f of x to be g of x minus a plus x. This is not that hard to get from g to f. I'm subtracting a constant and I'm adding x. If x is a fixed point for f, then f of x equals x. But f of x is g of x minus a plus x equals x. Or g of x minus a equals 0, or g of x equals a. So if I have a machine that gives me fixed points, I can use that to solve g of x equals a. So the whole point here is that the ability to find fixed points is actually extremely valuable. I can convert a lot of problems to finding fixed points. And again, if you're interested, what's really lurking in the background of the triangle game is a fixed point theorem. And this fixed point theorem was used by John Nash, got him a Nobel Prize. in proving that in a large swath of games, you're going to get into these kind of equilibrium situations. Now, one thing you could do, we all agree the triangle game is like the rectangle game, it sucks. Yes. So what you can do is give students an open-ended question. Make the game better. So anybody have any thoughts as to what could we do, to make this game better? We know there's got to be at least one 0, 1, 2 triangle.
More than one.
Good. So I can only win now if there's more than one 0, 1, 2 triangle. So all of a sudden now I don't know if I can guarantee a win. Because maybe you can do it in such a way now that you can ensure, I only know that there's got to be an odd number of 0, 1, 2 triangles. As soon as you say that there has to be at least 2, we know that at least 2 becomes at least 3. Now all of a sudden I don't know if I can still win. The game now becomes interesting. So the question is, open it up. I've been in programs where they go prove, disprove, or salvage if possible. And so with the original rectangle game, we had to salvage it. It was really boring. You put down one square and then you're done. I give you an extra 1 by 1 tile, and all of a sudden, we can tile the whole plane and we get the Fibonacci numbers. For the triangle game, I could do it as, I have to have at least 3 0, 1, 2 triangles to win. Or if we play the line segment game, I could do it such that we count how many 0, 1 segments there are. And every time there's a 0, 1 segment, I get a point. Every time there's a 0, 0 or 1, 1, you get a point. Anything else we need to do? So you get a point for every 0, 0, every 1, 1. I get a point for every 0, 1. Do you think there's anything we need to do?
You should get every amount of.
Like 2 points for every 0.
Well, because I get 0, 1, and I also get 1, 0. So I've got 2 options, you've got 2 options. But what do we know about the number of 0, 1 segments? It's going to be odd, it's going to be at least 1. So maybe you can say, okay, I'll agree to your point system, but we have to subtract 1 from your total. Because we know you're going to guarantee to get 1. A handicap. And if you know some more probability, what you could do is you could say, what if we played a random game? And just put things down randomly. How many 0, 1 segments do you expect to get randomly? And maybe we use that to kind of come up with a fair compensation. So there's a lot of great game theory stuff that you can do. As much as possible, I love trying to get students to salvage. Okay. I want to make sure we have plenty of time for lunch, so I want to do just a few more things before we break. How many people do geometry? Okay, so I want to try to do a couple of geometry things. I know technically the class title is ALLgebra. If people are not happy with me doing geometry, I will just say a few algebraic words every now and then to try to justify this. But I have to be very careful as this is being recorded. All right. So these are 2 very famous lattices. One is the square lattice, one is the hexagonal lattice. During the pandemic response, I actually advocated that schools in Massachusetts switch to hexagonal seating. Why? Why? So what did we have to do during the pandemic response in the beginning when we had in schools 6 feet separation? So one question is, when you're looking at separation like this, each of these segments is 1 unit. If I do something over here, and each of these is 1 unit, can you get more people in a fixed area? So I'll leave this as an exercise for you to do. Yeah.
I did this.
Closer to the
You-
circle.
So again, we have to be very careful because this is being recorded.
I went to the office and I
Wait,
said.
let me hit, let me just. So computer malfunction in 3, 2, 1, resume. Okay, everything's been fixed now, excellent. And so this is a great exercise to give to the students and say, calculate how many people you can get in using a hexagon versus a square. Are there other shapes that would do better? What if we do things three-dimensionally? No, they're not gonna let us do that. Yeah. How many of you have seen the Lego movie? Yeah, what am I thinking of in the Lego movie?
The couch.
Yes, the couch, the double-layered couch, which turns out to be the only thing that survives. Right? What if we put our students three-dimensionally? No, we're not going to get away with that. But just, it's so easy to get caught up in what's always been done is how it shall always be done. And we always have people sitting in squares. I'm going to prove to you that most of us do not love our children, our students, or whatnot. And they won't love their children or students either. Who knows what this word means? Oops. Oh, sorry. QWERTY. It's keyboard. It's the keyboard. Why is the keyboard QWERTY?
It's the most common letter.
It's to slow down.
It's to slow down. In the old days of typewriters, if you hit two keys that were close to each other in quick succession, as they go to put marks on the paper, they would often jam. And so the typewriter is designed to slow you down. Because that would mean we would have to change. We would have to learn something new. So professional typists use the Dvorak keyboard. Even straight alphabetical is better than QWERTY. But it requires the people who have already learned how to do something to change. And so we just pass it on. But if you really kid, you would not use the QWERTY keyboard. You would teach a better keyboard than QWERTY. I assume everybody here has sent at least one email in their life. What does CC stand for in an email? I'm sorry? Carbon copy in an email? So some people have changed so that CC now has been changed to mean courtesy copy, so that you can keep the abbreviation CC. But it goes back to carbon paper, where you would write down hard and you would then have another copy that you could have. And so there are so many things that are just hardwired. You know, it's tradition, it's always been done this way. You know, we have to keep doing it this way. Every now and then, somebody will make a change. And again, life lessons for students. Any football fans here? Should you go for it on 4th down? Usually. And so the conventional wisdom has changed. For the longest time, people were terrified about going for it on 4th down. It is better to lose doing what is the accepted, established strategy than to increase your chance of winning by doing something that's considered unconventional.
Depends on where you are.
It depends on where you are. But a lot of people play it safe. I remember years ago, the Patriots were playing the Colts. And if the Patriots convert on 4th down, they win the game, they can run out the clock. They didn't, meaning got the ball with a short field, marched down, Patriots lost. And in one of his numerous, effusive, elaborate press conferences, chock full of detail, Belichick was asked, "Why did you do that?" He goes, "Gave me a better chance of winning." Next question. And the computer simulation supported him. It increased the chance of winning by about 6% to go for it on 4th down. It didn't work in that particular case. He had had enough success that he could get away with something like that. When you're early in your career, you can't. The tall grass feels the blade first. If you do something non-standard and you stick out, you are unfortunately putting your head on the chopping block. Anybody ever see the movie True Lies? So in the beginning scene, there's a special op that is a complete disaster. A lot of damage, a lot of explosions, and Charlton Heston, who is the head of the organization, is yelling at the 3 people behind it: Arnold Schwarzenegger, Tom Arnold, and young aspiring actor who has a small role. And Schwarzenegger and Arnold are joking with Charlton Heston. This is a whole level of screw-ups from. And then the third guy makes a joke at some point. And Charlton Heston looks at him and goes, "What makes you think the slack I give them extends down to your level?" And when you are in different places in your career, you can't get away with some things. And so those of us who can, we sometimes have to be the ones to push and say, let me have my kids sit like this. It's going to make a lot more sense. We can do some good. But you're going to face extreme resistance a lot of times. So to make this an algebra question, what you could do is you could imagine larger and larger squares and see how many students could you get in the different metrics and give this to the students to calculate. And you could ask, what if you do pentagons? Do pentagons fit together nicely? Equilateral triangles do, but equilateral triangles are really the same as a hexagon. Here's another one. How many of you did pooled testing? Your schools had kids test? And so I got to be very careful what I say about the choice to spend as much money as we did on testing. So the best you can do is test every person. What is bad about testing every person? It's a lot of tests, and why is a lot of tests bad? Money. It costs a lot of money. And time. And then you have all these tests that have to be sent off to the lab and analyzed, and you have to get the more tests you send, the longer it's going to take to get things back.
The kids don't take it seriously.
A lot of people don't take it seriously. Right, I mean, can you trust that they've actually done things properly? And if they haven't, a lot of times if you're doing surveys, you occasionally have strange questions to just see, is anybody paying attention? For this question, please circle C. And this is a chance to see. As you can tell, I love stories. Anybody know about Van Halen and the M&Ms? Okay, two people.
They wanted
Brown
specific
M&Ms.
color.
Yes. So Van Halen had in their contract that they had to be provided in the changing room with a bowl of M&Ms with all the browns removed. And when you first hear this, your response should be, what a bunch of pampered, and then this is being recorded, so I'll just leave it as that. They can't have a brown M&M. They're too good for this. So who knows why they had no brown M&Ms?
To make sure that the promoter was paying attention and reading the rider.
Yeah, to make sure that the contract was actually read, because they had some very heavy equipment, and if it's not put in correctly, it could actually fall and kill someone. Now, you could go up to people and say, pretty, please, will you please read the contract and make sure everything is done properly? Oh, of course, we always read things carefully. We always follow the contract. This allowed them to just quickly walk in, and if they see brown M&Ms, they know that the contract was not read. There was one time when they walked in, and there was an entire bowl filled with nothing but brown M&Ms, and they laughed. They got the joke. That was a nice response. But it's how do you know that what you are doing is actually being done the way you want? So as you said, just because they're taking the tests does not mean they're taking it accurately. So if you have a large school, let's say you have n squared people, that's n squared tests. That's a lot of tests to do. If something is very rare, you don't want to spend too much time testing for things. Imagine only one person is infected with COVID. If we do n tests, n squared tests, that's very expensive to find one person. Imagine we break everybody into two different groups. Everybody's in two groups. You're in your row and you're in your column. And what I'm going to do is I'm going to combine the samples. So I'm going to have n row samples and n column samples. And imagine only one person is infected. So I will have this person as the one person who's infected. This row test will come out, there's somebody infected in this row. We don't know who, but there's somebody. And this column will come out, there's somebody infected. We don't know who. Well, they only intersect in one spot. So there's only one person who could be infected. And now, instead of n squared tests, it's now just two n tests. That's a lot cheaper. What if I had two rows and two columns that were infected? Well, if you look at it, now there's four possible people who could be infected. One possibility is maybe upper left and bottom right are both infected. I could have exactly two people infected, and that would be consistent. I could also have three people infected. I could also have four people infected. All of those are possibilities. But now, by doing tests like this, if there's 4 people infected, I'm sorry, if there's just 2 people infected, I can now reduce to just doing 1 more test with 4. And so again, when resources are limited, pooled testing like this is terrific. And so it doesn't have to be the most advanced mathematics to be useful. And you can do, if you're trying to do quadratic functions, so how many of you are doing quadratic polynomials? You could do this as a cost to run our school with in-person classes during the pandemic. Do you want a linear cost or do you want a quadratic cost? How much of the school budget do you want going to testing? Now, there can be extreme dangers if people who are infected come in. And so the question is, how risk averse are you? And this is definitely not a conversation to have with things being recorded. But it's conversations that need to be had. And you have to decide, is it worth the risk? Is the probability low enough that I think this is acceptable? Or is the probability high enough that I can't afford to do this? If there are very few people who are infected, you do not want to be spending too much time and too much money on tests. And then, of course, also, if tests are limited, if masks are limited, you want to be very careful who you have them. I actually was able to get a bunch of masks in the beginning of the pandemic. I donated them to first responders to the school. And I was furious when I saw people wearing them as hats. This is not how a mask is supposed to be used. The last one, just for some geography, is a brief example of tomography. So imagine you have cancer cells and you want to discover where they are. One possibility is you open up the person, start slicing them, and look at them. I assume we all agree that this is a very bad idea. What do we do? MRI. So we send some high frequency, some radiation maybe through them. Now we want to send as little radiation as possible. And so the question is, I have Rubik's Cubes for many reasons. Let's say the Rubik's Cubes are the infected stuff. I can't make the Rubik's Cubes infected, that's wrong. I'll make the clementines infected. So if it's like this, so this I know is not going to be recorded that well by anyone. So if I look at something like this, if you look straight down, you would see the infected cell here, but you would not see this one, it would be hidden. If you look from this side of the room coming in, you would not see anything infected. If I look from the back, I do it like this so it's low, I would see the 2 things infected. And so the question is, how do I want to choose which directions I scan? And then when I get that information, how do I piece back where the infection is? So this is a little bit more on the geometry side, but I've written up stuff like this, or I have colleagues who've written up stuff like this. It's a fun exercise to do. And basically what you do is you have a bunch of count data in different directions, and you try to figure out what's consistent. And it might be the case that there are several different configurations that are consistent, very similar to what we had a moment ago. When I looked at the stuff over here, I could have up to 4 infected. Is it possible that only 1 person is infected of the 4?
No.
No. So I know there's at least 2 out of the 4 infected. But it could be 2, it could be 3, it could be 4, I don't know. And so when I'm doing stuff like this, and I'm doing my scans, which angles do I use to scan? Which directions do I scan? How many scans do I do? Do you maybe take some information and dynamically adjust where you do later scans based on what you're seeing? This area looks like it's pretty safe. This area looks like it has a lot of cancer. Let me do more scanning in that area. So a lot of times in life, you want to have things dynamic so that you can adjust as you're going along. Okay. Yeah. So like over here, maybe this is, I'm scanning from the front, and maybe the shaded things are all the things that I'm seeing is cancers. Sometimes people play a version of Battleship. I think there's a version of Battleship like this. I'll make the ships different colors. Okay. So I've got a bunch of ships placed. And let's assume I give you data of how many ship pieces are in each column. So maybe I give you 0, 2, 3, 2, 2, 2, 5, 1, 3, 1, 1, 1. If I give you data like that, is that enough for you to uniquely determine where everything is?
Yes.
What if I just tell you yes or no? So no, I'll do maybe nothing here, something, 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 something. That's not going to be enough information. And so the question is always, how can I get that information? How do I know that there's exactly 4 pieces in that? That's a different question. Imagine someone is giving you this data. What can you reconstruct from it? And you'll make certain assumptions. Maybe you'll assume you know which ships are on the board. You know the size and the number of each one of them, but you don't know the locations. If I give you something like this, is this enough? Or is it possible that I could give you a set of numbers where there's more than one configuration? Now, imagine I had a ship that was 2, a ship that was 3, and a ship that was 5 versus 5, 2, and 3. These are different configurations. In one, the 5 is on top, and the other, the 5 is on the bottom. I wouldn't be able to tell which of those 2 configurations it is, but I would still know which squares are occupied by ships. So again, whenever you have problems like this, you always want to look at extreme cases. And so just looking at this, I know I'm not going to be able to always uniquely determine where the fleet is. But I may be able to uniquely determine which squares are occupied by ships. So always think about which question do you think you can answer? Okay, so this is, I think, a good place to stop for lunch. I will try to work on getting things uploaded. We will resume at 1 o'clock. And then obviously, please feel free to bring food back here.